Blame it all on my roots. I showed up in boots and ruined your blind tie affair. The last one to know.
In this video, we'll talk about irreducible and prime elements in an integral domain. So this definition comes from section 8.3 of Dummit and Foote. So we've now moved into the section on unique factorization domains, but I won't actually say what a unique factorization domain is in this lecture. So let's say R is just an integral domain. Suppose little r is an element in the ring that's not 0 and is not a unit. Then R is irreducible in the ring if whenever R equals A times B, where A and B are in the ring, then at least one of A and B is a unit in R. So if R is not irreducible, then it's reducible in R. If you can write it as a product of two things that are not units. Two things, each of which is not a unit. Okay, so that's irreducible. What about prime? We know what it means for an ideal to be prime, but we haven't defined what it means for an element to be prime. So a non-zero element P in the ring R is prime in R if the ideal generated by this element is a prime ideal. Okay, what's another way to say that? That is, little p is prime if it's not a unit, because if it were a unit, the ideal that it generates would be the whole ring, and part of the definition of a prime ideal is that it has to be a proper ideal. So p is prime if it is not a unit, and if p divides AB, that means p divides A or p divides B. So now this matches up quite well with how you think of primes in the integers. One more definition: two elements A and B that differ by a unit. That is, you go from one to the other by multiplying by a unit. A equals U times B for some unit in the ring are associate in R, or they're associate elements, or they're associates. All right, so how do these concepts relate to each other? Proposition 10 in section 8.3 says that in an integral domain R, a prime element is irreducible. Okay, so prime elements are automatically irreducible. Let's prove that. Let's suppose that little p in R is a prime element. So the ideal that it generates is a prime ideal. We're going to suppose that you can write it as a product A times B, where A and B are elements in the ring. We want to show that P is irreducible. So what do we need to show? We need to show that at least one of A and B is a unit in the ring. Okay, so that's the name of the game. So we have to show that A is a unit or B is a unit using the fact that the ideal generated by P is a prime ideal. Okay, well, what's one thing that we know is in this ideal generated by P? P is in the ideal generated by P, and P is equal to A times B. So since the product A times B is in the prime ideal, the ideal generated by P, that means A is in the ideal generated by P, or B is in the ideal generated by P. Okay, so now we have some choice to make. Let's just say that A is the one that's in the ideal generated by P. If B was in there and A wasn't in there, you'll see exactly how to modify this argument. Just switch the A's and B's that you see everywhere. So let's just say now that A is in this ideal. So what does that mean? A is in this principal ideal generated by P. So A is equal to P times something. A equals PR for some R in the ring. And now, okay, so what do we know? A equals P times R, and we also know that P equals A times B. And now this should feel very similar to a situation we found ourselves in one of the arguments of the last video. So I'm going to pause and erase and complete the details of this proof. Let's complete this proof that in an integral domain, a prime element is always irreducible. So we had our prime element P. The ideal it generates is a prime ideal. We suppose that P equals A times B, where A and B are elements in the ring. Since AB is in this prime ideal, A is in the ideal or B is in the ideal, we said, let's assume that A is in the ideal, and it'll be clear how to modify things if, in fact, B was in the ideal and A wasn't. So, okay. So that means that A is equal to P times R for some R in the ring. So now we're back in the situation of one of the arguments from the first video, which is we know P equals A times B. Let's go up here to finish the proof. And A is equal to P times R. So P is equal to P times R times B. And since we're in an integral domain, you subtract P from both sides, use the distributive law. That means 1 minus R times B is 0. RB equals 1. And we're in a commutative ring. So RB equals 1, BR equals 1. That means that B is a unit in R. So what did we show? We supposed that we could factor P as a product of two things in the ring, and then we proved that one of those things has to be a unit. And that proves that P is an irreducible element in the ring. Okay, so we know that in any integral domain, a prime element is automatically irreducible. Well, what about going the other way? If you're an irreducible element, are you prime? And in a PID, these two concepts are the same. So proposition 11 says that in a PID R, a non-zero element is prime if and only if it is irreducible. And since we know that if you have a prime element, it is irreducible, all we have to do is show the other way, that irreducible implies prime in this ring R that is a PID. All right, so how are we going to do that? Let's suppose we have an irreducible element. We want to show that the ideal it generates is a prime ideal. And now the order of these results is very carefully chosen. What we're going to use is the fact that because we're in a PID, the way that we're going to show that this is a prime ideal is, well, in a PID, being a prime ideal and being a maximal ideal are the same thing. So we're going to show that this is true by showing that the ideal generated by this little p is a maximal ideal. Okay, so I'll pause and erase and finish the details of this argument. Let's finish this proof that in a PID, every irreducible element is prime. Where were we? We have some irreducible element P. We want to show the ideal it generates is prime. And we know that in a PID, the prime ideals and the maximal ideals are the same. So we can do this by showing that the ideal generated by P is a maximal ideal. All right, now this is very similar to something we did in the previous video. Let's suppose that you have an ideal I that contains this ideal generated by P. Since R is a PID, how to think about this ideal I? Well, it's generated by M for some element M in the ring. And now we want to prove that the ideal generated by P is a maximal ideal. So we want to show that either this ideal generated by M is the ideal generated by P, that these are the same, or the ideal generated by M is the entire ring R. All right, so what do we know? We know that the ideal generated by P is contained in the ideal generated by M. So the element P is in the ideal generated by M. So P is in this principal ideal. That means P is equal to R times M for some R in the ring. And now, for the first time, let's use the fact that P is an irreducible element. Here we've written P as a product of two things that are in the ring. So since you have an irreducible element, one or the other of these things has to be a unit. So one of those things is true. Either R is a unit, but if R is a unit, then the ideal generated by P and the ideal generated by M are the same because one of these things differs from the other by a unit. All right, so if R is not a unit, then that means M is a unit. But in that case, the ideal generated by M is the entire ring R. So what have we seen? We have seen that the only ideals containing this ideal generated by P are the ideal generated by P and the whole ring itself. Therefore, this is a maximal ideal, which means it's a prime ideal. So this irreducible element P is a prime element. Okay, so where are we? We know that in any integral domain, prime elements are irreducible elements. And we know that if your integral domain has this extra special property of being a principal ideal domain, that in fact, irreducible elements and prime elements are the same. So I'm going to pause and erase, and then I'll show you that it's not true that in every integral domain, those two concepts are the same. I'll give you an example of a ring that is not a PID. in which we'll see an example of an element that is irreducible but is not prime. In a PID, irreducible elements are always prime. But it is not always true that irreducible elements have to be prime. So the last thing I want to do in this video is give an example. Let's say that R is equal to Z adjoin square root of -5. And recall that we have this norm function on this ring that comes from the field norm in Q adjoin square root of -5, where the norm of a plus b square root of -5 is a squared plus 5b squared. The important thing to remember is that this function is multiplicative and that we can characterize the units in this ring in terms of this norm function. This function is clearly takes non-negative integer values, but the only way to get 0 is to apply it to 0. So it's a positive norm. And we proved in section 7.1 that a plus b square root of -5 is a unit if and only if the norm is equal to 1. More generally, in these quadratic rings, we saw that you're a unit if and only if the norm is equal to plus or minus 1, but minus 1 can't happen here. Okay, so the claim is that 3 is an element of this ring that is irreducible in R, but it's not prime. So let's prove that in two pieces. So first, 3 is irreducible. Let's suppose that we had a factorization, 3 equals alpha times beta for some alpha and beta in this ring. Taking norms of both sides of this equation, the norm of 3 equals 9, and the norm of alpha times beta is the norm of alpha times the norm of beta. So this norm is a non-negative integer, and alpha and beta, neither one of these can be 0, so in fact is a positive integer. And we know that the norm of R equals 1 if and only if R is a unit. So that means that if we had a factorization, 3 equals alpha beta, where alpha and beta were both not units, then we would have to have two numbers that were not 1 that both divided 9. So the only way for that to happen is if the norm of alpha equals the norm of beta is equal to 3. But there are no elements in this ring of norm 3. A squared plus 5b squared just doesn't take the value 3 when you apply it to integers. A squared plus 5b squared has no integer solutions. So that's it. There's just no possible way to factor 3 into a product of two non-units because there's no way to take a product of two non-units and get something of norm 9. Okay. Why is 3 not a prime element? So it is irreducible. Why isn't it prime? Well, if you take 2 plus square root of -5 times 2 minus square root of -5, you get 9. And that is in the ideal generated by 3. So we have a product of two things that's in the ideal generated by 3, but I claim that neither one of these things is in the ideal generated by 3. So this ideal is not prime because we have a product A times B that lands in the ideal, but A is not in the ideal and B is not in the ideal. So let's just check that this is true. How do we know that 2 plus square root of -5 is not in the ideal generated by 3? Well, what does it mean to be in a principal ideal? Well, if you were in this principal ideal, then you could say that 2 plus square root of -5 was equal to 3 times something, where that something is in your ring. So it's A plus B times square root of -5 for A and B, two integers. But that would mean that 3A equals 2 and 3B equals 1, and there just are not integer solutions to those two equations. Okay, so similarly, exact same setup, you'll see that 2 minus square root of -5 is not in this ideal generated by 3. Okay, so what have we found? In this ring, we have an element that's irreducible that's not prime. And that gives a proof that Z adjoint square root of -5 is not a PID. Because in a PID, this can't happen. Every element that's irreducible is automatically prime. So I think this is pretty neat because we've seen another way to see that a ring is not a PID. We didn't do anything here to produce an ideal that's not principal, right? We've just proven that here's an element that has some property that elements are not allowed to have in PIDs.